This episode is brought to you by Brilliant. The pistons within the 2023 Mercedes-AMG F1 M14E Performance Power Unit represent the bleeding edge of internal combustion technology. With just a mass of around 220 grams, they routinely withstand forces exceeding 10,000 Gs, exemplifying the extreme performance demands of modern Formula One racing. Operating within an engine that can achieve thermal efficiency above 50%, a feat unheard of in conventional internal combustion engines, these pistons function in an environment that redefines the limits of material science and mechanical engineering. With the engine capable of reaching speeds up to 15,000 RPM and generating combustion pressures estimated to exceed 300 bar, these pistons endure thermal and mechanical stresses that would destroy conventional components almost instantaneously. Even more remarkable is the thin strip of metal that forms the critical link between combustion and the incredible horsepower in these engines, while still retaining the basic design of early engines from a century ago. The first internal combustion engine pistons were directly derived from external combustion reciprocating steam engines, which initially were made from wooden plugs sealed with either leather or tarred fiber rope. By the late 1800s, cast iron would become the primary material for steam pistons, with cast iron rings being used for sealing. With the introduction of internal combustion, the environment in which these pistons operate would require an entirely new approach to transferring expanding gases into rotational motion. Steam engine pistons seldom experience temperatures above 500 degrees Celsius or pressures above 25 bar. They also operate at low speeds, often far below 1000 RPM, and often in a double-acting motion in which both sides of the piston are driven. Oil-based lubrication is also easier to achieve in these engines due to the lower temperatures and pressures, which permit the presence of oil within the cylinder without significant degradation or loss. The first internal combustion engines of the mid-1860s, such as Jean-Joseph-Étienne Lenoir's double-acting coal gas engine and Nicolas Otto and Eugene Langen's rack and pinion-based free piston engine, both used atmospheric-based low compression, allowing for the use of a single cast iron piston and rings derived from steam engine designs. However, by 1876, Otto and Langen would pioneer the four-cycle engine, the first internal combustion engine that compressed the fuel mixture prior to combustion. This technique almost tripled the efficiency when compared to atmospheric engines, but at the cost of dramatically higher cylinder temperatures and pressures. Though Otto and Langen's early four-stroke engine design operated on a compression ratio of just 3.5 to 1, it developed cylinder temperatures and pressures that were at the upper limits of existing steam engines. Pushing past this would quickly reveal the ceiling limitations of early piston design. The first modern metallic split-ring seal concept was invented by John Ramsbottom in the 1850s. Ramsbottom's initial attempt at piston sealing was to simply replace existing organic material with a split circular cast iron ring. However, the shape made the seal uneven. By 1855, he would revise the ring to an out-of-round shape so that it would exert even pressure once installed in the cylinder. The switch to iron piston rings had the benefit of dramatically reducing the frictional resistance when compared to organic materials, and could easily be stacked to reduce the leakage of steam. It was also far more durable, increasing maintenance intervals. By the mid-1880s, the first high-speed multi-horsepower four-stroke gasoline engines suitable for transportation would be introduced. With compression ratios now approaching 6 to 1 and the introduction of splash oiling systems, piston sealing would ultimately coalesce into the modern multi-ring configuration where the topmost rings, known as compression rings, seal combustion gases, and the bottom ring, known as the oil control ring, directs the supply of oil towards the cylinder wall but away from the combustion zone. The overall design of a piston ring is guided by several key properties that determine its mechanical behavior under operation. Piston rings are designed to have a larger diameter in a relaxed state than in its installed state. This is necessary to create the required contact pressure on all sides in the cylinder and is known as tangential tension. It's quantified as the tangential force required to pull the split joint ends together into a specified clearance. Tangential tension is also a factor in specific contact pressure, or the force exerted by the ring on the cylinder wall per unit of contact area. Either doubling the ring tension or having the contact surface of the ring will double the specific contact pressure. In piston ring design, specific contact pressure is always a compromise between sealing and friction. This principle is particularly relevant in modern engine designs, where the trend is moving toward thinner ring heights to reduce internal friction and increase fuel consumption. A ring's radial pressure distribution must also be considered. This property is the measure of how the ring's outward force is spread around its circumference when installed in the cylinder. There are two main types of pressure distributions: symmetrical, where equal pressure is applied around the ring, and positive oval distribution, where a higher pressure is applied at the ring's split joint ends. This distribution is influenced by the ring's material elasticity, joint clearance, and cross-section. While symmetrical distribution is ideal for sealing, positive oval distribution is often employed to reduce dynamic issues such as flutter at high speeds, which typically start at the joint ends. The metering of contact pressure due to combustion pressure is another crucial aspect of piston ring function. During engine operation, up to 90% of the total contact force on piston rings come from combustion pressure. As combustion occurs, high-pressure gas is pushed behind the rings, forcing them more firmly against the cylinder wall. This effect is strongest on the topmost rings and diminishes for lower rings. This increased contact pressure enhances sealing performance during the most critical part of the engine cycle. This gas pressure movement to the lower rings is metered through joint clearance, with larger clearances allowing for more combustion pressure to pass downwards, increasing overall sealing. As you move lower in a modern piston sealing system, the function of a piston ring transitions from gas sealing to oil control. The primary property that determines this functionality is the piston ring's profile. Both early piston rings and modern topmost gas sealing rings use a basic rectangular profile. Known as a compression ring, they seal by forming a high surface area path that progressively traps combustion gas flow. This trapped gas also expands the ring against the cylinder wall, and in some configurations, even reshape the ring. This shape is both easy to manufacture and allow for good contact with the cylinder wall for sealing. These rings also dissipate around 55% of the heat that is absorbed by the piston during the combustion process to the cylinder, forming an integral thermal management component of combustion. By the second ring, oil control features start to appear in ring design. This is primarily accomplished through oil scraping against the cylinder wall on a downward stroke, while hydrodynamically riding over the oil on an upward stroke using a shaped contact edge. One of the earliest forms of oil control is the taper-faced ring. This simple extension of the rectangular ring has a conical surface that slopes inward, typically at an angle of 1 to 2 degrees from rectangular, and it can be found on modern engines as both a hybrid compression ring or as an intermediate piston ring. When new, these rings only contact the cylinder at their bottom edge, creating high contact pressure during the break-in period. The angled surface allows the ring to scrape oil more effectively during the piston's downward stroke. As they wear, they become less effective at oil control, though this wear also forms a rounded rectangular shape that increases its gas sealing properties. By the mid-1920s, more sophisticated features were experimented with in piston ring design in order to dynamically improve oil control while still maintaining good gas sealing characteristics. From this, ring twisting proved to be an efficient solution. By imparting a bevel or a step feature on the inner ring edge of a piston ring, it is deflected to the weaker side when in installed tension, creating a twist. Under combustion pressure, the twist flattens out, creating an ideal gas seal. But as this pressure reduces, the twist returns and the ring begins to function as an oil scraper. The twist of the ring is determined by the location of the bevel or step. If placed on the top edge, it creates positive ring twisting, while on the bottom edge, it creates negative ring twisting. Positive twist rings offer good gas sealing and oil scraping, but may allow some oil passed during the piston's downstroke. Negative twist rings are better at preventing oil from entering the ring groove, especially during partial load operation and engine braking, making them more effective at reducing oil consumption. However, they require a slightly larger sliding surface angle to compensate for the twist. Positive twist rings tend to be best suited for topmost compression sealing use. In the 1930s, English engine manufacturer D. Napier & Son would introduce Napier rings and Keystone rings, two styles of rings that would further enhance the control of materials within the combustion chamber. Napier rings are designed to enhance oil control with the inclusion of a rectangular or undercut recess on the bottom edge of the piston's sliding surface. This recess creates a small reservoir where scraped oil can collect before flowing back into the oil pan. Napier rings combine gas sealing with effective oil scraping, making them useful as secondary compression rings in many engine designs. An improved version, the taper-faced Napier ring, adds a conical sliding surface to increase oil scraping efficiency. This design is so effective that it can be used even as a topmost compression ring in some engine designs. In such cases, a closed joint design is used where the undercut doesn't extend to the ring's end, improving gas sealing performance. Keystone rings were specifically developed to combat carbon deposits in piston ring grooves, a common issue in high-temperature environments like diesel engines. These rings have angled sides, usually at 6 degrees, 15 degrees, or 20 degrees, giving them a trapezoidal shape. This unique profile allows the rings to mechanically clean the grooves as they move, preventing carbon buildup that could cause ring sticking. Keystone rings are typically used in the top ring groove of diesel engines and sometimes in the second groove as well. It is important to note that Keystone rings require matching grooves in the piston and cannot be used in standard rectangular grooves. Their cleaning action helps maintain proper ring function and engine performance in high soot, high temperature conditions. During the late 1910s and 1920s, oil control rings emerged in high-end automobiles as engineers sought to improve engine efficiency and reduce oil consumption. Luxury brands such as Cadillac and Duesenberg were among the early adopters, though more affordable vehicles like the Ford Model T, despite its popularity and long production run, did not initially feature them. As manufacturing techniques improved and the benefits became clear, oil control rings gradually made their way into more vehicles, and by the 1930s, they had become a common feature in most automotive engines. Oil control rings are designed to regulate the oil film on the cylinder wall and scrape excess oil back towards the crankcase. They typically have two scraping lands to compensate for the rocking motion of the piston. As the ring moves downward, each land scrapes oil off the cylinder wall, creating oil volumes both on the bottom edge of the ring and between the lands. Oil control rings have either longitudinal slats or bores between the ring lands where oil is guided through to the rear side of the ring. From there, the scraped off oil can drip back into the oil pan through drainage bores, either on the inner side of the piston or via a channel or bore on the outside of the piston. The oil drainage rate is metered by design so that a volume of oil is maintained between the lands and is redeposited as a 1 to 3 micron film on the cylinder wall on an upward stroke. The earliest oil control rings were simple one-piece designs with either a beveled or flat rectangular scraping lands and oil slits for drainage. These proved to be too inflexible for piston motion and would be superseded by two-part designs. Two-part rings improved upon flexibility by adding a spiral expander spring behind a single-piece ring body. The spring provided tension, pressing the ring against the cylinder wall. This design offered better conformability to the cylinder and more even pressure distribution. Derived from aviation engine development during World War II, the three-part ring would soon surpass the two-part ring and would slowly be adopted by the automotive industry post-war as the standard configuration for oil control, particularly in passenger vehicles. Three-part rings have two thin steel rails pressed against the cylinder wall by a spacer expander ring and are highly conformable and wear-resistant. Since their inception, piston rings have been made primarily from gray cast iron materials, which include both traditional lamellar graphite cast iron and modern nodular cast iron. In lamellar graphite cast iron, the graphite forms flat, flake-like structures which offer better wear resistance and thermal conductivity, while in nodular cast iron, the graphite appears as spherical nodules, making for both a stronger and more durable material. These materials can be either annealed or heat treated to increase ductility or non-annealed. Gray cast iron is preferred for its good elasticity, corrosion resistance, oil retention within its structure, and emergency running properties thanks to graphite deposits that act as dry lubricants. For most of the 20th century, engines that operate under high stress or require enhanced durability utilize steel for piston rings, particularly chrome steel with a hard, strong crystal microstructure formed by rapid cooling, and spring steel. To enhance wear resistance, steel ring surfaces often undergo nitriding, a heat treatment process that diffuses nitrogen into the surface to create a very hard layer. Steel is also commonly used in multi-part oil control rings, as thin steel rails for the scraping edge, which may be chrome-plated or nitrided on all sides for superior wear resistance. The expander spring in multi-part oil control rings are also typically fabricated from heat-resistant spring steel, which maintains its elastic properties at high temperatures. While cast iron has excellent sealing properties, the relative softness of the material when compared to other metals would soon become a limiting factor in engine life. The advent of hard chrome plating in the late 1930s allowed cast rings to achieve almost 3 times greater face hardness. Applied using galvanic processes as either a full face, an inlay, or a semi-inlay coating, it provides a high durability, hard, non-sensitive surface that prolongs engine life. It does require a longer engine break-in period to establish a working surface, often requiring a more aggressive bore surface finish to aid in this break-in. It also lacks the dry lubricating properties of a cast iron surface for emergency use. The 1960s saw the introduction of molybdenum coatings that offer a balance between the surface properties of cast iron and chrome. Applied via flame or plasma spraying, molybdenum has a high melting point of 2,620 degrees Celsius and offers excellent temperature resistance while being softer than chrome, making it easier to break in. The coating's porous structure allows oil to collect in microcavities, providing lubrication under both extreme and emergency conditions. However, they do suffer from coating detachment in cases of poor installation or extreme cylinder conditions. By the 2000s, manufacturers started to chase more fuel-efficient designs that required an inherent reduction of friction within the engine. With this, thinner piston rings were required. The brittleness of iron limited how thin they could be manufactured. This resulted in the development of a thin, phosphated, or copper-plated steel ring that featured physical vapor deposition face coatings that apply hard material layers like chrome nitride directly onto the ring's surface. These coatings minimize friction loss due to their extremely smooth surface and offer high wear resistance. Physical vapor deposition coating rings can maintain their contour longer, allowing for reduced ring tension and improved friction characteristics. Chrome ceramics and diamond coatings were also introduced around the same time period. These consist of a galvanized chromium layer with a network of cracks in which hard materials like ceramics or microdiamonds are embedded. These coatings provide minimal friction loss, maximum wear resistance, and low wear on both the ring and cylinder. Ultimately, piston ring design comes down to several critical dimensions that must be considered, each affecting performance, break-in, and friction. The ring height and radial wall thickness influences the ring's stiffness, inertia, and fluidity. Lower heights and thinner walls reduce friction, but may compromise sealing ability. The free gap, or the ring's opening when uncompressed, determines the ring's tension and its ability to conform to the cylinder at operating temperatures. The joint clearance when installed affects gas sealing and gas blow-by. Ring height clearance in the piston groove is crucial for proper movement and gas pressure buildup behind the ring. The specific contact pressure, determined by ring tension and contact surface area, impact sealing and friction. Higher pressures improve sealing but increase friction. The sliding surface shape, whether flat, tapered, or crowned, affects oil control and break-in times. Coatings and surface treatments alter the effective dimensions and impact wear resistance, friction, and break-in characteristics. Additionally, the design must account for thermal expansion, ensuring proper function and free movement across the engine's operating temperature range. On the extreme end of the spectrum is a Formula One engine. Titanium expanders are paired with ultra-thin steel tungsten carbide coated rings that are just 0.5 to 0.7 millimeters thick, with only one compression ring and one oil-controlled ring. These rings are designed with joint and groove clearances so tight that they do not fully function outside of the engine's operating temperature and require aggressive oil cooling to thermally manage their operation. Their overall operation places the focus on uncompromised gas sealing with minimal friction. Today's vehicles also employ thin ring designs combined with thinner synthetic oils in the pursuit of better fuel economy through lower friction. Though in many cases this results in longevity issues as well as a dramatic increase in oil consumption, with many manufacturers accepting the usage of a quart of oil every 1,000 miles or about a liter every 1,600 kilometers as acceptable. Currently, both regulations and market demands for greater fuel economy are propelling the development of thinner rings with more advanced coatings that permit even lower friction, though these design compromises may bring pistons back into the realm of being a primary longevity failure point as they once were a century ago. While material sciences have contributed significantly to engine development over the past century, the fundamental advancements in engine internals have been largely driven by the evolution of key geometric features. In piston rings, for example, small changes in the profile geometry dramatically impact engine performance and longevity. Systematically approaching design challenges with an eye towards geometry is a critical skill, and a great way to build a strong understanding of this approach is Brilliant. Brilliant is where you discover the thrill of learning with thousands of captivating interactive lessons in math, data analysis, programming, and AI, designed to unleash your potential and transform you into a confident problem solver. Brilliant is a groundbreaking educational platform that distinguishes itself by employing a first principles methodology, empowering learners to construct a robust understanding of fundamental concepts. Every lesson is filled with interactive problem-solving exercises, encouraging active participation and engagement with the subject matter, a method proven to be 6 times more effective than passively watching lecture videos. Furthermore, Brilliant's content is crafted by an esteemed team of award-winning educators, researchers, and industry professionals from renowned institutions such as MIT, Caltech, Duke, and prominent companies like Microsoft and Google. Brilliant immerses you in active problem-solving because truly grasping a concept demands more than mere observation and memorization. You need to experience it. You'll not only build real knowledge on specific topics, but also develop critical thinking skills that make you a better thinker overall. Investing in daily learning is paramount for personal and professional development, and Brilliant makes this convenient and enjoyable. With captivating, digestible lessons that seamlessly integrate into your daily routine, you can build genuine knowledge in just a few minutes each day. Say goodbye to aimlessly scrolling and embrace a more rewarding way to spend your free time. A great way to become a skilled geometric problem solver I highly recommend is Brilliant's measurement course. In this series of lessons, you'll build intuition for geometry fundamentals, from angle axioms to 3D shapes, using logic to solve increasingly complex problems while learning how to apply them to real-world problems. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/newmind or click on the link in the description below. You'll also get 20% off an annual premium subscription.